Okay. So, ordered pairs are different than sets, okay? So, if you have an ordered pair, okay. So, if you're not talking about a set and you're talking about an ordered pair, order matters, okay? So, when talking about sets, okay? For a set, AB equals BA. It's just element A and element B. Okay? But with ordered pairs, AB does not equal BA as long as B and A are different. Okay. So where are ordered pairs really used? Well, obviously they're used in a ton of places. But the Cartesian coordinate system, we're going to talk about Cartesian products here in just a second. But if you consider, instead of talking about an element A and an element B, and then you're talking about AB and BA, well, think about it this way. Those are obviously not the same points. Okay? So there's this difference between sets and ordered pairs because they're not interchangeable. I mean, if you had 1, 1, well, 1, 1 equals 1, 1. So if they're the exact same thing, then yeah, you can switch them, whatever. But in general, no, you can't just switch them around. Okay? And so you can even go into higher things where if you said, let's say, 1, 2, 3, 4 does not make equal 1 or 2, comma. Okay. So when talking about ordered pairs, order untuples, whatever, yeah, the order is really important. Okay. All right. Now we're going to talk about how we actually create ordered pairs. Because with ordered pairs, we start off with sets, and then we create ordered pairs from those sets. And the way that we do this is through the Cartesian product. And so, this is going to use the same type of notation that we were using just on the previous video for when we were defining sets. So, the Cartesian product cross A2 is equal to, so if we do a Cartesian product of two sets, this will be the ordered pair A1, A2, and then such that A1 is in A1 and A2 is in A2, or that A1 is an element of A1 and A2 is an element of A2. Okay, so the Cartesian product is a way to form ordered pairs. And now, if y'all have seen the name Cartesian before, what would you think of the Cartesian plane? Okay? And why do we call this the Cartesian plane? It's after René Descartes, who was a philosopher who basically kind of came up with the Cartesian plane, although it's debatable. Another thing you might know Descartes from is the famous quote, "I think, therefore I am." So Descartes was the one who said, "I think, therefore I am." It was actually the first part in a three-part argument for the just. Never mind, I'm not going to put this on YouTube. Okay, so all right. So what if we did the reals across the reals? All right, so what would this be? This would be the Cartesian coordinate system, which would be x, y, such that x is in the reals and y is in the reals. All right. And that forms our normal Cartesian coordinate system. Let's say we wanted to take this into higher dimensions though, okay? Because the world is not flat unless you're reading Flat World. What if we did so if we do r cross r, we end up with x, y, z, where all the x's, the y's, the z's are in R. And so that would give us three-dimensional space. So the Cartesian product can extend into higher dimensions. And if you want to go even further with this and extend it all the way into the nth dimension, there's no problem with that. So everybody's supposed to get caught up. So if we decided we're going to do r let's say we did this n times, we would end up with a set x1, sorry, x2, all the way up to xn, such that x sub I is in R. I'm kind of running out of room, so I had to squeeze it down there. Okay, and what this is known as an n-tuple. And instead of thinking about this as in terms of dimensions, like obviously I showed you R2 and R3 representing two-dimensional reality and three-dimensional reality. And if you want to go into R4 and view time as another dimension of reality, yeah, that's totally fine. But why, in other places, why would we use n-tuples? Well, we can actually just use n-tuples as not talking about dimensions. The normal way you see these ordered pairs is related through dimensions, but it actually can just represent n variables with whatever system you're dealing with. So instead of talking solely about dimensions and talking about two-dimensional space, three-dimensional space, stuff like that, you can get into just talking about variables, okay? And that's actually what a lot of set theory and stuff deals with, is just dealing with a lot of variables. So let's look at how we would treat some of these variables. Okay, so let's try a different set. Let's say A is going to equal 1, 2, 5. Let's say B equals S comma T. Okay, so here we have two finite discrete sets. Okay? And so we're going to look at how we represent these sets. Okay? So, A cross B would equal the set. Okay, I'm going to write this. Remember, the ordering doesn't matter when you're talking about the set. The ordering does matter when you're talking about the ordered pairs. So, when talking about the ordered pairs, A always has to come first, okay? So, let's start off like this. So 1s, 1t, 2s, 2t, 5s, 5t. All right. Now let's look at B cross A. Sorry, a little off the screen. So A cross B does not equal B cross A. So this is an example of an operation which is non-commutative. So A cross B does not equal B cross A versus our normal idea of multiplication. And there are actually a lot of operations within mathematics that are not commutative, meaning if you do it forwards and backwards, it does not mean the same thing, okay? One of the main ways that you'll notice that multiplication is not always commutative is if you multiply matrices, which we'll do in this class. Matrix A times matrix B does not necessarily equal matrix B times matrix A. Okay, well, all right, see, but this is a little confusing to look at, just writing down a bunch of ordered pairs. So a lot of times we want to draw these as mappings, okay? So instead of drawing this out as a set of ordered pairs, let's draw this as a mapping from one set to the next. Because remember, when we talk about ordered pairs, and when we talk about functions, in mathematics you say, well, we have f of x. The function eats x and spits out y, okay? That's what's meant by order when we have these types of operations. So if we draw this, instead of this way, let's say, and we're going to spend a lot of time drawing these relationships in different ways. So if I say, all right, I want to draw a picture of what A cross B is, okay? Now, if I have A right here, say 1, 2, and 5, and B right here, which is S and which is T. Okay, so now for A cross B, all of these mappings are going to go together. And we'll spend some time later on drawing these maps and asking the question, is this one-to-one, is it onto, or other ways to phrase this, is this injective, bijective, surjective? Those are some definitions that we'll get into later on too. And this will also give us the relationship of what is a function versus what a relation. But if we reverse this and we said, all right, what is B cross A? Well, that would be S would map to 1, S would also map to 2, S would map to 5, T would map to 1, T would map to 2, and T would map to 5.